To compensate for the last lecture, which I admit can be a bit traumatic, this one is going to be much shorter and lighter, and basically we are just going to tie some loose ends before moving on to more unsupervised learning topics, which we are going to start next week. So this is just to wrap up the supervised learning part. And so I'm going to talk basically about two things. One is a brief mention of Bayesian learning. We are not going to cover Bayesian learning in any depth in this course, but just to give you an idea that this exists and a brief notion of what it is. And then we're going to look at more practical problems of deciding based on the results of our classifiers, of our machine learning, and pondering about also the costs of the different options and including that in how the decisions are made. So let's start with Bayesian learning. We saw that to find the parameters for our models, we maximize the likelihood. That is the likelihood of the parameters is the probability of having that data with those class labels given that we have the parameters. So we have some parameters here. We compute the probability of the data and the classes, and this gives us the likelihood of the parameters. Sorry. So we want to maximize that likelihood. That is to say, we want to find the set of parameters that gives us the highest probability estimated for the data that we have. So what we did basically is we rewrite these joint probability distributions as conditional probabilities, and we have the conditional probability of being in some class if it has some features, multiplied by the marginal probability of the features. But since the probability of the features is something that has no relevance for the classifier, we then simplify this and we basically maximize the conditional probability of whatever it is that we want to predict, some class label, some continuous value, given that we have those features for each set of parameters, and we change the parameters until we find the maximum there. So this is a frequentist interpretation that we followed. In that, probability is the frequency of some random event in the limit when we do infinite trials. So since the parameters are not random variables, they are values that we are changing, and the best parameters is just some value, that set of values that we're trying to find. So these are just additional parameters that we're putting there, but they do not count in the probabilities. A Bayesian interpretation is different. Unlike a frequentist interpretation, the Bayesian interpretation of probabilities does not assume any metaphysics about the universe. It does not assume that things may be random or not random or things like that. The idea is that we are considering probabilities to be an expression of uncertainty about something. It doesn't matter if that something is truly random or just unknown, or even if there is no difference between the two. We just are expressing knowledge and uncertainty. So we can consider that the parameters we're trying to find are also have a probability distribution, because that expresses the uncertainty about what those parameters are. So we can consider that we start with a prior probability distribution for our parameters. They are more probable in some range of values, less probable in other ranges, and so on. We have a sample of data, and now what we're going to do is update this probability distribution for our parameters, given that we have this data. And we can do this with Bayes rules. So the probability distribution of our parameters, given that we have this sample of data, is given by the probability of the data being like that given the parameters, multiplied by the prior probability for the parameters, and divided by the marginal probability for the data. So we can consider this to be the evidence we have for the new parameters. This probability here is actually the same as the likelihood that we found before, because it's the probability of the data given the parameters. But the whole thing is a bit more complex because now we are taking into account explicitly some probability distribution for the parameters that gets updated as we encounter the data. So this forces us to take into account explicitly this prior probability distribution. We can still do the same kind of approximation here. So in this case, we discarded the probability, the marginal probability of the features here, and focused only on what was relevant for our classifier or our model to optimize the parameters. And so we maximize this conditional probability for maximum likelihood. We can do something similar in the Bayesian approach, where we maximize the a posteriori in this case by ignoring the probability distribution of our sample. So we generally don't know what is the probability distribution of the data, but we can focus on the rest. But the big difference here is that while with maximum likelihood we are just computing the probability of the data given some parameters and then fitting the parameters in order to increase that probability, so the probability of what we want to predict given the features and fixing the parameters. In this case, we are multiplying by a probability distribution for the parameters, and this and we have a joint probability distribution here between the data and the parameters. So this generally requires a lot more computational power. So we need to compute these priors. Usually the prior distribution, it's best to make it as uninformative as possible, and this may require some complex computations, and usually this is done by Monte Carlo, by simulations and so on. So Bayesian learning requires a lot more computational power than in general the frequentist approach that we saw. But one big advantage is that what we saw with this approach, the frequentist approach for maximum likelihood, is that we can benefit by including regularization terms that try to fiddle with this set of parameters so that it doesn't grow too large or something like that. So we saw those regularization terms that we had. So we are not just maximizing the likelihood, but we are maximizing some cost function that includes not only the likelihood, but also some penalty for if the parameters grow too large or something like that. And this is a bit ad hoc. We are experimenting with different functions just to fiddle with things to make it improve. And the Bayesian approach has this advantage that we do not need to do that in such ad hoc fashion, because we can explicitly say what is the prior probability distribution of the parameters that we are assuming. And this works exactly as the regularization term, but it has a much more clearer meaning in the approach. It's not something that we just add on, it's something that is part of the whole way of understanding the search for the parameters under uncertainty and the whole idea of probabilities as expressing uncertainty. Okay, so we are not going to actually do this, but I wanted to mention this different aspect. It both at the level of probabilities of the theory and also in computation, it's more demanding, but it can be more powerful and it can help with some problems by giving us a more formal way of making explicit these assumptions instead of just, for example, experimenting with regularization and some ad hoc changes. Okay, so the other aspect I wanted to cover now is the problem of making decisions based on what our classifiers are telling us. So basically, we've been always assuming that the goal is to minimize the error. So we've been working with different ways of measuring the error, but the idea is that if we have a classifier, we want the classifier to make as few errors as possible. And our loss functions are basically like that, measuring some aspect of the error and that we want to minimize. But now let's suppose this example. Suppose that we have these joint probability distributions of some feature x, just one dimension, and being in class 1, and x and being in class 2. Let's say it's something like this. So this is the probability distribution of x and class 1, and this is the blue one is for x and class 1, the black one is for x and class 2. So class 2 is more prevalent on this side, class 1 is more common here. And suppose that we have a very simple classifier that just looks at x, and if x was larger than some threshold value, it belongs to class 2, and otherwise it belongs to class 1. So basically we are drawing this line here, and we're saying on this side we have class 2, so this is correct, this here is wrong. This would be the cases of class 1 that we are classifying as class 2. And on this side we have class 1, and so these will be correct, and this part will be wrong because these would be the class 2 examples that we are classifying as class 1. If we want to minimize the errors, the classification rate, we are basically trying to maximize the probability of x belonging to the correct class. So in this case, we can do this if we choose the threshold in a way that we assign to class 1 all examples that have a larger probability of being in class 1 than of being in class 2, and we assign to class 2 all examples that have a larger probability of being in class 2 than being in class 1. So basically, if we draw the line here, we minimize the errors, because on all the region that it's larger for class 2, we assign to class 2, and in the region where it's larger for class 1, we assign to class 1. So this is the general approach we've been following so far. We want to minimize the error. But now suppose that class 1 is cancer and class 2 is healthy. So class 1 is cancer patients, class 2 are healthy people. If we look at the problems of making a mistake in the prediction, we see that the cost is not the same, because if a healthy person comes in and we have a false positive and we predict that this person has cancer, okay, that's probably quite a scare, but then we do some additional testing and so on, and we see that it was a mistake, so not a big deal. However, if a person has cancer and we send her home saying that everything is okay, don't worry, then she'll die of cancer without treatment, and this will have a much higher cost. So we can see that it's not a symmetrical problem, because mistakes are much costlier in one case than in the other. So now, what do we really want to minimize? It's not just the probability of making a mistake, but it's actually the cost, or the expected cost, of mistakes. And so we need to multiply this probability, this loss, depending on what happens, with the probability of making the mistake. And this is what should be our loss function. So what we want to minimize is not just the probability of making mistakes, but the probability of making a mistake multiplied by the cost of that mistake. And that's what we want to make as low as possible. So if we do this, this would be minimizing the classification error, but this does not minimize the cost of the mistakes. If we take the loss into account, we go into this different region, which actually we can see if we multiply the probabilities by the cost, this would be such that the cost below this threshold would be smaller. That is the cost multiplied by the probabilities of mistakes for these classes, and after this threshold. This is a very simple example. This is not a real classifier. We would not make a classifier like this, but this is just to illustrate that the actual loss function is not just the error rate, but the error probability multiplied by the cost of making mistakes. And this would be more reasonable, more useful for making actual decisions than just trying to minimize the error without taking into account the different costs of different mistakes. So we can see this in two different ways. So we can see this as a loss, the probability of the error times the cost of the error, or utility, so the benefit we get from not making a mistake in one case or in the other, or avoiding a mistake. But this is basically the same. It's just that we minimize losses and we maximize utilities, but we have basically the same general idea. It's just going into two different ways. What we the important message here is that we don't just want to look for the smallest errors. We actually want to minimize the costs of those mistakes. Okay, so this is one problem, maximizing the utility or minimizing the cost. Another problem is how confident we are about the recommendation, about the conclusion or the result of our system. Because it may be the case that we don't want to make a mistake, but we don't know exactly how to avoid that, and we can just postpone the decision. So we may want to postpone the decision until we are more certain of what we are doing. And in that case, we can try to reject the whole classification when we see that there is not much certainty in what our classifier is doing. So, for example, we can reject classification if the probability of getting the classification correct is below some threshold. For example, suppose that if we have examples that are far to this side, then they are clearly class 1. We don't make much mistakes there. If they are on this side, they are clearly class 2. But if they are here between the two, we are not very sure. In this part, they are more class 1. In this part, more class 2. But there is quite a lot of uncertainty here. We could have our classifier classify things as class 1 if they are on this region, as class 2 on this region. But if they fall in the middle, the classifier says, I'm not sure. So I don't give a classification, you decide, or something like that. So this would allow us to avoid some places, some regions where the error may be more likely. And if we don't want to make mistakes, this could be an option. So to sum up this part, this was just to wrap up the supervised learning part. Next week, we're going to start looking at some away from supervised learning, and we're going to look a bit at visualization of data and feature extraction, feature selection, and so on. So some things will still be related to supervised learning, others will start into unsupervised learning, but we'll be moving on to the second part of the subjects we are looking at here. So if you want, you can read in Alpiden and Bishop these sections about Bayesian interpretation, Bayesian learning, and also these decisions. Okay. I will now change everything and go to the Zoom meeting if you have any questions.